The B-tree node splitting mechanism operates as a fundamental structural rebalancing routine within sorted index storage systems. When a node reaches its configured maximum capacity threshold, the split operation allocates a new sibling node and distributes keys and associated value references across both nodes according to a deterministic midpoint selection algorithm. The parent node is updated to reflect the new key boundary. This process maintains invariant tree depth properties across all leaf paths. Node capacity is defined as a system parameter denoted node degree max, typically set between 16 and 256, depending on storage block size and key width. When insertion operations cause the key count to exceed node degree max-1, the split routine is triggered before the insertion completes. The midpoint index is calculated as node degree max divided by 2, rounded towards 0. Keys below this index remain in the original node. Keys above are transferred to the newly allocated sibling. The promotion key, which separates the two child nodes in their parent, is selected as the element at the midpoint index. This key is copied upward into the parent node at the appropriate insertion position, determined by binary search over existing parent keys. If the parent node also reaches capacity during this promotion, a recursive split operation cascades upward. When a root node splits, a new root with two children is created, incrementing the overall tree height by 1. Value pointer arrays are redistributed alongside their corresponding keys. If the node is an internal node, child pointers must also be split. The first half of child pointers move with the lower keys, the second half with the upper keys. The midpoint child pointer becomes a reference from the parent to the right sibling. Internal node children maintain their relative ordering to preserve search invariance. Leaf nodes have no child pointers, only keys and value references. Memory allocation for the new sibling node uses the standard allocation routine from the underlying buffer management layer. The allocation maintains page-aligned boundaries for efficient disk I/O. Once allocated, the new node is initialized with node type flags, depth metadata, and a 0 key count. The original node's key count is updated to reflect the number of keys it retains. Both nodes are marked as dirty and scheduled for persistence in the write-ahead log. The split operation exhibits time complexity of O log n for tree navigation and OM for actual key redistribution, where m equals the node degree. Practical performance is bounded by the I/O cost of persisting modified nodes. On systems with sufficient buffer pool capacity, multiple internal nodes may reside in memory, reducing I/O operations. The amortized cost across repeated insertions is O log n because splits are triggered infrequently relative to standard insert operations. Edge cases within the split mechanism include splits occurring at the root node, which necessitate root replacement and height increment. Splits on minimum capacity nodes occur when node degree max equals 2, a valid degenerate configuration functionally equivalent to a binary search tree. Splits involving keys with duplicate values require consistent ordering policies. Ties are resolved by record identifier or insertion sequence to maintain predictable ordering across all instances. Concurrent access to B-trees during split operations requires coordination through the distributed lock manager. A split acquires an exclusive write lock on the affected node and its parent. The operation is atomic from the database's perspective. Either the split completes fully and is logged, or it is rolled back to the pre-split state. If a concurrent transaction attempts to access the affected subtree, it waits for the lock release. Lock timeout is configurable with default value of 120 seconds. Logging of split operations occurs in the write-ahead log as a single log entry containing node identifiers, key ranges before and after redistribution, and metadata flags. The log entry is assigned a sequential log sequence number and written to persistent storage before the split is considered committed. On recovery, the log is scanned and split operations are reapplied to restore tree consistency. Incomplete split entries are rolled back using stored and due information. The split function signature in the C API is defined as int split node btree handle, node ID parent, node ID target, size t split position. The function returns 0 on success or an error code indicating resource exhaustion, lock timeout, or log full conditions. The split position parameter allows callers to specify custom split points, though the default midpoint selection is used when split position is set to the reserved constant auto midpoint. Performance tuning of the split operation involves adjustment of node degree max to balance tree height against node size. Higher degree values reduce tree height and search cost but increase split redistribution overhead. Lower values result in taller trees with more node traversals but faster splits. Empirically determined optimal values typically range from 32 to 128 for systems with variable length keys. Degree selection should account for expected key and value sizes. The split mechanism interacts with the buffer pool through the get page and mark dirty functions. When a split completes, both the original and new sibling nodes are marked dirty. The buffer pool eviction policy respects pin counts during split operations, preventing premature eviction of nodes being modified. Unpinned nodes may be evicted between split phases if memory pressure is sufficient, causing the split to be restarted. This restart behavior is transparent to the calling transaction. Statistics collection for split operations is managed by the Query Optimizer module. Counters track total splits executed, splits by tree depth, and average keys redistributed per split. These statistics inform index maintenance scheduling decisions. When split frequency exceeds a configured threshold during a maintenance window, index rebuild or compaction may be triggered to restore optimal structure. Threshold defaults to 50 splits per million insertions. Under extreme load conditions where the buffer pool capacity becomes insufficient to hold all modified pages pending flush, the split routine implements a backpressure mechanism. New splits are queued in a priority heap and executed during low activity windows. This prevents cascading out of memory errors during bulk load operations. The queue timeout parameter, split queue max delay, defaults to 5,000 milliseconds before forced abort. Recovery procedures following system failure validate B-tree structure through checksum verification of split log entries. The recovery process walks the tree from root to leaf, comparing key distribution against split log records. Inconsistencies trigger repair routines that redistribute keys according to logged split information. Full tree validation is performed only on database startup when recovery mode is enabled. Incremental validation runs during normal operation at configurable intervals. This concludes the technical specification for B-tree node splitting mechanisms. Implementation details including lock acquisition order, buffer management integration, and log format specifications are covered in subsequent sections of this manual. Readers requiring information on deletion-triggered merge operations should consult Section 4.3. Detail, pseudocode, and performance benchmarks are provided in Appendices C and D respectively.